So, we have seen cases where it is required for us to differentiate with respect to vectors, with respect to matrices, etc. So, this is often encountered in signal processing. For example, a simple case would be a form of a scalar which is x transpose x, right. Imagine x is a column vector. So, therefore, x transpose is a 1 by n row matrix and x is a n by 1 column, I would say row vector. This is a row vector, this is a column vector, okay. And we may want for some instance to take the derivative of alpha with respect to x. So, we may need d alpha by dx. So, how to go about problems of this form, and this is particularly useful when we deal with representing problems vectorially or in the form of matrices, and then we have to take derivative of some function of vectors and matrices and compute these quantities, and this becomes a non-trivial task. So, unless we know how to play around with the algebra, we will often get stuck, and if we do in a routine way, we will have to really do this as scalar derivatives over each element by element computation. So, we will figure out some intuition behind how to go about doing this matrix calculus, and then this will be useful when we discuss for example in KL transforms. We will find this often helpful. Okay, this is an old concept, nothing really new, but I would like to give you some idea here. So, we can differentiate matrix quantities with respect to the elements in the reference matrices, and often this is done using the Jacobian matrix. So, there are certain conventions. I will present to you an intuition how this works, and then we can discuss certain properties. Okay. So, let us just start with an example. So, consider A times x. So, y is some A times x. Suppose A is a 2 by 2 matrix and x is a column vector, and this is a suppose 2 by 1, right. So, let us just compute these quantities. A is A11, A12, A21, A22. This is our standard notation, right. The first row first column, first row second column, second row first column, and the second row second column, and then we have x1 x2, these are the elements of this vector x, right. So, I just put this bar underneath y and x indicative that they are vectors. Okay. Now, if you compute this, this is a11 x1 plus a12 x2, this is a21 x1 plus a22 time x2, and this is the vector y composed of elements y1 and y2. Now, let us adopt one convention, which is basically the Hessian rule. So, if I want to take the derivative of y with respect to x, so that means I am trying to differentiate, I am differentiating the vector y with respect to x, and this is given in this format. This is d bar y 1 upon d bar x1, then d bar y2 upon d bar x1, that is I vary in the row, I vary the coordinates of y, that is I choose y1 y2, and then I take y1 I differentiate with respect to x1, I choose y2 differentiate with respect to x1, so on and so forth. Similarly, the second row I look at y1, take the derivative with respect to x2, then look at y2, take the derivative with respect to x2, and you may really question, I mean, should I go this way? You do not have to. For example, if you look at a different format, then you can take y1 d bar y1 by d bar x1, you can choose d bar y1 upon d bar x2, and so on and so forth. So, this is a different convention. So, there are two different conventions. One convention basically keeps the first coordinate of the vector constant in the row and then take the derivative. You can follow this convention here, which is basically the denominator layout, and I mentioned this sort of carefully. As long as you are consistent, it is fine. So, you basically keep the y coordinate fixed in the, I mean the x coordinate fixed in the denominator, and you let the y coordinate basically vary within the row, that is across the columns. So, this is the convention that we will follow. So, now if you take the derivative d bar y1 upon d bar x1, this is basically a11, and d bar y2, if you take the derivative of y2 with respect to x1, you get a21, and similarly if you populate the rest of the entries, you get a12 here, you get a22 here, and observe that this matrix is basically the transpose of A, right. So, we can formulate a rule here, that is, if I want to differentiate the quantity Ax with respect to x, so x is a vector, I get A transpose. But of course, you should remember the convention, which is basically we are following denominator layout, and your calculus has to be sort of consistent. I mean, if you are basically varying y in the row and keeping x fixed, then you should be consistent with respect to that. You do not want to mix, once when you differentiate you want to have y varying, other time x varying. I think that should not really happen. Okay. Now, let us take another example. This would be a good example for us. Consider x transpose Ax. You will see this form in many cases. Okay. Now let us look at the math for working out this example. Now let x be a 2 by 1 column vector. Okay. Now x transpose is a 1 by 2 row vector and A is our 2 by 2 matrix like in the last example. So again this is a scalar, x transpose Ax is a scalar, like possibly think about x transpose x is a scalar. I mean if you just multiply you know instead of x transpose x I have x transpose Ax, and this is a scalar. You will find this form, this quadratic form, in many signal processing applications. So let us just get an intuitive feel how this works. So suppose we are interested in taking the derivative with respect to x of the quantity x transpose Ax. Okay, let us work out the math, just as routine computations to get a feel, an intuitive feel how this works, right. I have x1 x2, this is my x transpose, right. So this is my x transpose. Now my A is A11, A12, A21, A22, right. This is my A, and my x is basically x1 x2. Now if I compute this quantity, right, I get basically x1 x2. Let us do an interim step. So Ax is basically what we had earlier, which is A11 x1 plus A12 x2, then we have A21 x1 plus A22 x2, right. When we simplify this, this is basically x1 times A11 x1 plus A12 x2 plus x2 times A21 x1 plus A22 x2, right. Now we will adopt the same convention. Let us differentiate the scalar with respect to x1 and x2, right. So earlier case we had a vector and we were differentiating that vector with respect to another vector. Now we are differentiating a scalar with respect to a vector. Now derivative of x transpose Ax by dx. So this can be done as follows. This is basically derivative of, so let me call this quantity here you know the scalar as eta, just for convention. So this is basically eta here. Okay. So now we have d eta by d bar eta by d bar x1, and then you have d bar eta upon d bar x2. If you work out this carefully, you will end up with the following. This is going to be 2 times A11 x1 plus A12 x2 plus A21 x2, and then you have the other term which is A12 x1 plus A21 x1 plus 2A22 x2. Now let us try to rearrange this. Right, we will land up as follows. We have A11, A12, A21, A22. You can just verify this, that it is going to be of this form. So you have to have 2 times A11 that has to appear, and you have one term here and you have another term here, right. I think this is straightforward to verify. So now this can be written as AX plus A transpose X, so which is basically A plus A transpose times X. So if A is symmetric, that is A equals A transpose, right, then derivative of X transpose AX with respect to X is going to be 2 times A times X. So I think it's a standard result. Now you will find this form very helpful when you deal with calculus. I mean, I just gave you an intuitive feel how you can do this for a 2 by 2 matrix and a 1 by 2 vector, and you can sort of generalize this to A, which is an n by n matrix, X being a n by 1 column vector, and X transpose being a 1 by n row vector, and the results are pretty straightforward. Okay. So let us see one other case. I will give you an example again. Consider another example where I want to take the derivative with respect to X of some product of 2 vectors u and v, right. So let us form this scalar which is u1 u2 times v1 v2, right. You could call this possibly u transpose, following the same convention that we followed, right. Now eta in general is say u1 v1 plus u2 v2. There are 2 different vectors. Now if you are interested in taking the derivative with respect to X of the scalar eta, then you will end up with the chain rule as follows, right. So it is u1 deba v1 upon deba x1 plus v1 deba u1 upon deba x1 plus u2 deba v2 upon deba x1 plus v2 deba u2 upon deba x1. So just carefully observe that I kept this x1 fixed throughout in the derivative, right. I assumed this form. So this is basically the denominator layout. Now the second term of course would be u1 deba v1 upon deba x2 plus v1 deba u1 upon day by x2 plus u2 day by v2 upon day by x2 plus v2 day by u2 upon day by x2. So, if you rearrange the terms carefully, right, let us try to do that. You will get day by u1 on day by x1, day by u2 on day by x1, day by u1 upon day by x2, day by u2 upon day by x2, and then you will have a vector v1 v2 here. Similarly, you will have one more matrix. As you can similarly imagine, this is going to be the vector u1, the vector u comprised of u1 and u2, and you can think of day by v1 upon day by x1, day by v2 upon day by x1, day by v2 upon day by x2, and day by v2 upon day by x2. This is v1 here, day by v1 upon day by x2, day by v2 upon day by x2. Okay, so this is basically written in the form day by u upon day by x times v, the dot product dot times v plus day by v upon day by x times u. Of course, we have to see that this is not the dot product, it is just a normal multiplication. Okay. You will find this very useful. So, I think now since you have gotten a feel, an intuitive feel how to go about doing the calculus, I will give you some quantity, so a table comprising of these derivatives. You can just directly verify those as a part of a homework exercise, and basically you can convince yourself that these results are correct. Okay. So, let me summarize. Some rules of matrix differentiation. Okay. Now, let us see the quantity and then the result. Right. First is a is a constant, that is not a function of x, and if I am interested in day by a upon day by x, the result should be 0. Then we saw that day by ax, x is a vector upon day by x, and this is A transpose, and you could do the other way around, you could take x transpose A, right, that is another possibility. If you did day by of x transpose A with respect to day by x, you should get A here. Okay, two different variations, A and B. Then day by x, A times u, where u is some function of x and is a constant matrix. you get day by u upon day by x times A transpose. Then we have this important result, day bar of x transpose Ax upon day bar x. This is A plus A transpose times x, and when A is symmetric, it is equal to 2Ax if A is A transpose, that is for symmetric matrices. So, I think using these basic rules for doing matrix calculus, it is very easy for you to take a derivative of a scalar with respect to a vector, scalar with respect to a matrix, and so on and so forth. And we will explore these results when we discuss some optimization that requires taking derivatives of certain quantities with respect to vectors. Okay. So, with this we conclude some basics on matrix calculus that is required for your mathematical methods.